Hello everyone. Now, as you probably know already, I actually have two Udemy courses specifically for teaching you how to look at and mastering the fundamentals of electrical transformers. So one of them is teaching you how to understand power transformer fundamentals, how to spec it, what are the things you can look out for. And the other one is more or less focusing on diagnostics and testing. Now, none of these actually include calculations in what you need for designing transformers. So in this case, here we are. I have created this video where I'm going to teach you how to actually calculate transformer calculations so you have enough to design a three-phase transformer from start to finish. Now, if you haven't check out my Udemy courses pertaining to transformers fundamentals and testing and diagnostics, I urge you to go visit my link in the video description for these two courses and see if you're very interested in building up some fundamental knowledge for yourself and your career. So now, what are we going to go over in this video? Well, in this video, we will calculate the apparent power, finding out the core geometry, finding out primary and secondary turns, as well as line and phase current. We're also going to calculate the primary and secondary bare wire area and wire resistance, as well as looking at primary and secondary losses. Now, the end goal of all of these calculations is so that you could spec your primary and secondary wires. It's for you to also find total losses, watts per kilogram, as well as transformer efficiency, watt per unit area, and finally the temperature rise. So as you can see here, it is going to be a lot of calculations. So if you want, you could follow through in this example, as I'm actually going to go over quickly an example, a model example, just so that you could know how am I calculating these values. Now, these values, a lot of them are actually make-believe. I'm not actually relying on real data, but instead I'm just showing you how these formulas work. So if you want to go through with me in this problem, I recommend you to actually take out a piece of paper and pencil and probably a calculator or spreadsheet tool for you to calculate. And you should actually start to write some of these input down. I would recommend you to even to actually pause this video and just jot these make-believe data right now, as I'm going to use this input data to actually go through my calculations. So now, this is only the first part of the input that you need. As you can see, you actually need a lot of data before you go into calculating in the transformer design. So first of all, with the design specifications, we would need the input voltage, which is Vn, and this is around 200 volts. Again, this is make-believe data again, so none of these are actually real data. And then also we got output voltage, which is VO, which is 20 volts. We also got output current, which is IO, which is 5 amps. Our output circuit is actually what we call a full bridge circuit, and our winding orientation is going to be delta delta. Now, I'm providing you this in a sense that you don't really need this in this example, but I'm going to refer to some of the values that I use and some of the values that I use is actually reference to the reason behind I'm using this type of winding configuration in a transformer. So you probably wouldn't use it in this problem, but in the future of the values that I'm going to use, it's basically a reference to the real data of these type of transformer configuration. Now, of course, frequency, we're using 60 hertz. Efficiency, we're going to aim at 95%. The regulation or alpha, we're going to put it as 5% in this example. Now, flux density, we should design this in this particular case. We're going to design it to 1.1 Tesla. For the window utilization or KU, we're going to set this at 0.3. And for the diode drop or VD, we're going to set this as 0.5 volts. Now, with the core specification that we want the iron weight to be 2.5 kilograms. The mean length turn, which is the MLT, is 15 centimeters. The iron area, which is, we call it the AC, is 6 centimeters square. The window area, or WA, equals to 30 centimeters square. The area product, or AP, we're going to set it as 250 centimeter to the power of 4. The core geometry, which is kg, we're going to put it as 40 centimeter to the power of 5. Now the surface area, or A, we're going to set it as 700 centimeters square. The primary window of utilization, which is KUP, is 0.2. The primary wire chosen resistance is going to be 1000 micro ohm per centimeter, and the secondary wire chosen resistance would be 150 micro ohm per centimeter. Now, the last two entries, I have to say, is basically of me being a oracle, meaning that we are going to have two imaginary wire in which in this sense your wire that's going to be chosen based on what you calculate is going to have this kind of resistance. Now, in real life, what you need to do is after you calculate the things I tell you to calculate, then you look at these cable spec reference tables to reference the cable that you need, and then read the specs and give you the chosen cable, or sorry, the chosen wire resistance. However, though, because this, as I said, it's a make-believe example, we're going to pretend that we already know what we choose, and here is the chosen resistance, which is 1000 micro ohm per centimeter for the primary and 150 micro ohm per centimeter for the secondary. Now the last three values that you need, again, these are all make-believe values, are the core loss equation coefficient factors. And they are the capital K, M, and N. Now K in this case would be 0.00056, M would be 1.7, and N would be 1.9. Now these factors actually differ from the core material as well as what type of core that you choose. And the values I'm using right now is of fake values. I'm not using any real values in this case because I'm just trying to teach you how these calculations work. So in a sense, if you are doing your transformer designs, again, you need all of these information before moving on to your calculations. And in a sense, if you you need to actually use a lot of reference material in order to get these information. So if you're actually doing real transformer design, be sure not to use my input values. So now, after we get all of these values, you have jotted all of these down, let us begin with our calculations. Now, if you are interested in learning more about electrical transformers or gaining a more fundamental and comprehensive knowledge base of electrical transformers, I recommend you to sign up to my Udemy course called Electrical Transformers Fundamentals. Now, this is a comprehensive video course where you can learn all about electrical transformers that are essential in working within the industry, from basic knowledge to how to procure and install transformers. So if you're interested, please check out the link in the video description. Now, with our transformer design, we should calculate our apparent power first. But with apparent power, we need to calculate our output power, which is PO. Now, our output power PO has the formula of IO, or output current, times V naught, which is the output voltage, plus 2 times the diode drop voltage. Now, in our case, with the example, will be 5 times 20 plus 2 times 0.5. In this case, if you plug in the formula, it will be 105 watts. Now, with the output power, we can calculate the apparent power, or PT, in our equation, which is PT equals to PO times 1.05 over N plus 1.05, where N is the efficiency. So if we plug this into formula where efficiency equals to 0.95, it will equate to 226 watts. So now after the apparent power, we should actually look at the calculation of core geometry according to our design spec. Now our core geometry, or KG, we need to actually calculate a variable which is called the electric condition, or KE. Now KE is equal to the formula of 2.86 times F squared times B squared times 10 to the power of minus 4. Now F is the frequency and B is the flux density. So you plug in those values, it equates to 1.25. Now then you could plug in the KE, or electric condition, into the core geometry formula, which is KG equals to apparent power over 2 times KE times alpha, where alpha equals to regulation percentage that's given in the problem. So now you plug in all of those values in, it equates to 18.17 centimeter to the power of 5. Now, the values that you see here and the values that are continuing on in this video might not match to what you calculate. And the reason being is because even though the results I gave are actually rounded, I actually use Microsoft Excel to actually calculate all of these. And with Microsoft Excel, we actually didn't round any of these values. So in other words, you might see slightly different numbers than what you do if you calculate yourself. But as I said earlier, take this as a very idealistic approach and take this as a non-real approach. What I'm showing you is the process. What I'm showing you is the formulas, but the values I'm using and the rounding is actually not too important in this sense. I'm just showing you how, but I'm not showing you precisely on actually what it needs to be done in order to get the correct answer. So even if you see that these numbers deviate, don't stress it too much. So the next section that we're going to calculate on is how are we going to select the primary wires. Now, before that, we need to know the number of primary turns that we need, which we can use the formula NP equals to input voltage times 10 to the power 4 over 4.44 times flux density times AC, which is the core iron area, which I already given to you, and times the frequency. So now you plug all of those numbers back in. You should have something equate to 1138 turns. Now, with the number of turns calculated, you could calculate the primary line current, which you use the formula PO, which is the output voltage over 3 times the input voltage times the efficiency, which you get as around 0.184 amps. But you don't your main goal is not to calculate this. Your main goal is to actually calculate your phase current, which is your line current divided by root 3, which is equals to 0.106 amps. Now, with that in mind, you also need to calculate your primary bare wire area, or AWP, which is equal to your KUP, which is your primary window utilization, which I already gave you, times WA, which is the window area, which is also given, over 4 times your number of primary turns. You plug all of this formula in, you would have 0.001319 centimeters square. Now you can use your phase current and your bare wire area to actually finally spec your primary wire. Now, with specing a primary wire, you should basically use those parameters and look up on a table of some sort to find out what is the actual wire that you want for your primary. Now, with that in mind, you should have something called a wire resistance. So remember that I tell you in the input table that normally you would get the wire resistance right now, but instead I give it to you in the table in the given section, just so because this is actually a make-believe scenario and I'm just arbitrarily giving you a wire resistance. And what you need to use with that wire resistance is you need to calculate your primary winding resistance, and in the end, you need to calculate your primary copper loss. So with primary winding resistance, this would be equal to your MLT, which is your mean length run, which is from the core specification in the given table, times the number of primary turns, times the wire resistance that you just spec, times the 10 to the power of -6 just for the unit conversion. And when you plug in all of those values in the given table, you should have something equate to 17 ohms. Now with this, the winding resistance, in the end, you could also calculate your primary copper loss, which is equal to 3 times your phase current squared times your winding resistance. You plug all of those back in, it equals to 0.579 watts. So with this, we're done with the primary for now, and so now we should actually move on to your secondary side. If you want to learn more about electrical transformers, particularly in testing and doing diagnostics, I recommend you to check out my Udemy course, Electrical Transformers Testing and Diagnostics course. Now, this is an intermediate video course where you will learn all about electrical transformer troubleshooting that are essential in working within this industry, from general failure investigation methods to specific transformer tests, such as the dissolved gas analysis. So if you're interested in electrical transformer testing, troubleshooting, etc., please check out my course by clicking on the link in the video description. Now, with the secondary voltage side, your secondary voltage can be calculated using the formula 0.74 times VO plus 2 times VD. Now, as with a lot of these values that are going on, the arbitrary values, you might be questioning now why is 0.74 specifically, right? Well, these factors are actually based on your transformer configuration. So in this case, remember what I said about in the given table that the configuration that we're using is delta delta. Well, 0.74 is a factor that we use in this formula, and this is actually the factor for secondary voltage per lake, particularly with delta delta transformer configuration. And this factor will be different depending on what type of transformer configuration you use. So if you are actually designing your transformer, be sure to actually look at the IEEE, the IEC standards for these formulas, and then look up the table in terms of what kind of factor that you need to use. Because again, there are a lot of options in terms of transformer configuration, in terms of the material of the core that you need to use, as well as the core surface area, etc., etc. So in this sense, be sure to check out the IEEE and IEC standards. And if you doubt which ones that you need to refer to my transformer fundamental course, as I would have a list of the standards that you actually need to review in order to become an expert in transformers. So with secondary voltage, now continue on to the secondary voltage formula. You have 0.74 times V, the output voltage, plus 2 times your diode voltage drop. You plug in all those numbers in, it should equate to 15.54 volts. Now you need that secondary voltage to get your number of secondary turns, which is similar to your primary turn, but the formula is quite different because your formula is actually based on your primary turn and your primary voltage. So in this sense, your formula is actually your primary number of primary turn times your secondary voltage over your primary voltage times your 1 plus regulation percentage over 100, which in turn equals to 92.8 turns. Now with the number of secondary turns, again, it's the same as how you do your primary side, which is you first need to calculate your line current, which is your 0.471 times your output current. Again, the reason being is because it's a specific transformer configuration, and this is a factor to be used. So again, this might change, so look at your IEEE or IEC standard if you need to spec your own transformer and design your own transformer. So with that, you plug into the formula, which is equate to 2.355 amps, and of course your phase current is just divide that by root 3, which is 1.36 amps. Now, of course, similarly as to your primary current, the whole purpose is to calculate the secondary bare wire area, which is equal to your KUP, which is your primary window utilization, times your WA, which is your window area. Both of these are given, over 4 times your number of secondary turns. Now you plug in all of those numbers, it should equate to 0.01616 meters square. Now again, you can use all of these calculated, like your phase current and your bare wire area, to calculate your to actually spec your secondary wires based on a table that's you could probably find it from your cable manufacturer or your vendor. Now, once you spec your secondary wire, in which, remember, I have already given you the wire resistance, which is 150, because this is a make-believe situation. So when you plug into the winding resistance formula, as I've done similarly with the primary winding, you would get, in this case, 0.209 ohms. Similarly, you could find, using the same formula as you did with the primary side, you could find the secondary copper loss to be 1.16 watts. Now, what you can use with the primary copper loss and the secondary copper loss is you can find total copper loss, and you could just add these two together, in which your total copper loss should be equate to somewhere around 1.737 watts. Now, your total copper loss, what you can do with it is to actually calculate your transformer regulation, which is equate to your loss over your output power times 100. So in this case, it would be 1.737 divided by 105. And this is calculated in the beginning times 100%, which it would equate to 1.65%. Now we are actually almost done. So we can continue on calculating the watts per kilogram, which is equal to the formula of K times F to the power of M times B to the power of N. Now, K, M, and N are actually coefficients based on the core that you choose. So it can be depending on the material, it can be depending on your core type as well. So these values would be different, and yes, again, these values are fake in this particular video because, as I said, I'm not going over an example to tell you the exact same solution of an actual transformer, but to show you the motions of how to calculate these for transformer design. So of course, F equals to frequency in this case, and B equals to flux density. You plug in the values from the input table in the beginning. It equates to 0.707 watts per kilogram. Now, what you use with this value is to multiply it by what we call the iron weight, which is given in a core specification in the beginning to calculate the core loss. And now if you plug into this formula, which is the watts per kilogram multiplied by the iron weight, it should equal to around 1.77 watts. Now, with the core loss and the primary loss and the secondary loss, you can finally calculate the total transformer loss, which you just add up your primary, secondary, and your core losses, and this should be equated around to 3.51 watts. And this is a very simple formula, it's just a sum of formula. And with the total loss, of course, you can finally find your designed transformer's efficiency, which the formula is pretty much very standard for all efficiency formula. In this case, it's your output power divided by your total power, which is your output power plus your losses, times 100, which is 105 over 108.51 times 100, which is equate to somewhere that is like 98%. Now, finally, I would stop with calculating the temperature rise. With the temperature rise, you need to have your watt per unit area, and you calculate that by having your total loss divided by your surface area, which I already gave you in the core specification. So you divide total loss over that. In this example, it should be around 0.005 watts per centimeter square. Now, lastly, calculating the temperature rise. So temperature rise would be 450 times the watt per unit area, which we calculated before, to the power of 0.826. Now, we plug in the 0.005 into this formula, it should equate to around 5.66 degrees Celsius. Now, this should actually cover most, if not everything, that you probably need in designing the transformer in itself. Now, as I said earlier, this is basically a make-believe set of data, and I'm just going over all the motions on the calculations that you need. Now, that doesn't mean that these calculations are exactly what you need in your design. As I've stated earlier, formulas, coefficients, values differs with the type of transformer that you are designing. So in a sense, I urge you to check out the IEEE and the IEC standards for transformers, because they would give you a step-by-step as well as sample calculations on what you need to do in order to design transformers. And I keep on emphasizing it to my students, and I keep on emphasizing it to people that I've worked with, consulted with, that the standards are very, very helpful for every engineer. And understanding standards is crucial in order to mastering the art of transformer design, transformer commissioning, anything to do with transformers. And I'm not just talking about power transformers, I'm talking about every single type of transformers that you could think of. Now, if you want to know which standards that you need to look at, I would urge you to sign up for my course, the Transformer Fundamental course. And if you're interested in troubleshooting transformers, doing diagnostics, and understanding transformer testing, I also have a course in Udemy as well. Both of them are actually in the link in the video description. So be sure to check that out. And if you like this video, be sure to hit like and hit subscribe to my channel, as I will produce new videos for you to help you understand more into the engineering concepts within the power world, within the energy world, and within the areas of sustainability and renewable energy. As I strongly believe that these are the things that would kickstart into the future. These things are very significant in the future, and it would definitely help you in beating your competition in your career. So again, if you're interested in learning more about transformers, be sure to sign up in my Udemy courses. My link to my course is in the video description of this course, and hopefully that you could subscribe to my channel and learn more about the world of utility, electrical engineering, and renewable energy. Thank you very much. Have a good one. I'll see you in my course and as well as in other videos. Thank you.